In this video, I want to introduce you to the notion of contour plots, or sometimes called level curve plots. Now, you may well be familiar with topographic maps. These are maps that show the terrain. There's all these lines drawn on it, and these lines are lines of constant elevation. So when you find one here labeled 3400, or maybe that's probably 8400, so that's 8,400 feet high. That's above sea level. Everything along that line, that curve, is 8,400 feet. You move to the next line and it's a different elevation. And not every one of these is labeled, but here's, this may be the 8,000 foot mark or the 9,000 foot mark. Anyway, every one of these lines corresponds to a constant height. It's like you have that mountain and you slice it with a plane at a particular elevation, and then you draw on the map where that slice hits the mountain. This is called a contour plot. Sometimes it's called a level curve plot. Each one of these curves is a level curve, or it's a contour. Both words are used. Okay. This is Mount Baker, by the way. I suppose you can see that. Some of you may have spent some time on these slopes. Some of the things I notice is that sometimes the lines are really far apart, and sometimes they're really close together. Well, if the contour plot is drawn in a particularly nice way, where it's the same gap each time, let's say every line represents another 100 feet of elevation or whatever it is, right? So when they're far apart, like when you're over here and the lines are pretty far apart, then that means a fairly gentle slope, right? Just going up, not very steep. But here, where they're close together, you're gaining elevation rather rapidly as you move along this slope. The lines are very close together, which means you're looking at something that's much steeper. Now, one of the things that might happen on an actual topographic map of a real place that will never happen on a contour plot of a function that we're going to be looking at is that the level curves, well, what we're doing, level curves will never cross. Because if two level curves cross, that means there's a spot that's at two different elevations, and that wouldn't be a function. Right? Real mountains can have overhangs, in which case you would have some level curves crossing. But our functions will never have overhangs. So here's the idea. Here's a function, z equals x squared plus y squared. It's a paraboloid opening upward, and I'm slicing it with the plane z equals 5. And you can see the slice there is a circle. And so that is the level curve, or the contour, of level 5. I could change the 5 to a 6 and it would move the plane up a little bit and it would be a slightly bigger circle, right? And each different elevation that I give, I would slice this thing in a different plane. This is all z equals a constant. The level curves are corresponding to the altitude, the z value equaling some constant. And in this case, they're always circles. Now, some books call, when it's here on the surface itself, they call it a contour. When you draw it like up here on the xy plane, then they call it a level curve. I've seen it both ways. I'm not particularly picky as to what you call it, contour, level curve. I will understand both ways. Right? So here is more level curves of that. So this is this paraboloid opening upwards, and I've drawn several level curves. Actually, I've had Mathematica draw several level curves for me. And one of the things Mathematica does by default is it colors in between the level curves, so you get a sense of what direction you're going. Apparently, down low is blue, and up high is more the, I don't know, what color is that? Peach? I don't know. Yellow. Note the comparison down here where I have an upside down paraboloid, and it still circles, and they look a lot like the previous one. However, because it's colored, you can tell that there's something different between these with the light color in the middle and the dark color out there, or this one with the dark color in the inside. So a lot of times what happens, in order to be able to tell whether you're looking at the top of a hill, like this one, or the bottom of a valley, like that one, the level curves are labeled. So they put a little number on the curve. Here's a 20, and a 30, and a 40, and a 50, and a 60, and a 70, right? That they tell you what the elevation is. That's what we saw on Mount Baker as well, that some of those level curves were labeled so we could tell what was what. Or, as Mathematica does here, they just color it, and blue apparently is low, and the yellowish is high, and so you can tell that's the bottom of the valley. I like this because the blue being low down, you'd expect to find water down in, if it rained out, there'd be water down here in the low spot. So here, where you got the mountains or the hilltop, if there's going to be water, it's going to be down on the edges there. So you see it here, there. So either label your axes, either label your level curves to be able to tell what they are, or color it somehow. Right? Now, to draw a level curve plot, you have to take your function. In this case, I have 10 minus x squared 10 minus the quantity x squared plus y squared, and I set it equal to different values for z. I'd set it equal to 0, and I'd look at what happened there. I'd set it equal to 1, I'd look at what happened there. And each time you pick a particular z value, then you're going to have an equation with just x's and y's and some numbers, and you say, what does the graph of that thing look like in the xy plane? Plot it. In this case, it'll always be circles. Right? Or it'll be nothing if you happen to get up high enough, if you get up above 10. Because if I said 11 equals this thing, well, this is 10 minus a positive number. Well, that's never going to get up to 11. So the level curve of level 11 is the empty set. There's nothing here that would be level 11. But if you pick the level 5, if you said 5 equals this thing, well, I'd move the x squared plus y squared to the other side and the 5 over here, and I'd have x squared plus y squared equals 10 minus 5, or x squared plus y squared equals 5, and that would be a circle of radius square root of 5, centered at the origin. And so you plot that one. And then you do a 6. You plot that one. Right? So you're just plotting different curves based on choosing different values of z. Notice that the level curves, as we pointed out, for low points and high points look kind of the same. They kind of circle in. I notice on Mount Baker up here, the top looks like, well, I can't really tell if that's because things are labeled, I can tell I'm headed uphill, and this is the top. But there's places in here, like there's the crater summit, that if you zoom in, there's a little low spot in here. Right? But there's other high spots here too. There's other smaller peaks. So peaks and valleys are reasonably easy to spot because of the kind of circular nature of them. They're not exactly circles all the time. And there's also another thing that's easy to see in the contour plots, and that's a saddle, something like a hyperbolic paraboloid. Here's the contour plot for this hyperbolic paraboloid. The grids you can see over here are the traces. So constant values of x give you, constant values of x are going this way, give you parabolas opening downward. Constant values of y are the ones going this way, parabolas going upward. So those are the traces. The contours come from constant values of z. So slice it this way, and you'd be intersecting in hyperbolas that match here, or lower down, you'd be hitting hyperbolas down here. So what I see low down, blue is low, remember? So these are low slices down here. And then you get up to the middle slice, which actually looks like two intersecting lines. It is. There's a line running right through the middle there, and a line running right through the middle there. That's the elevation 0. If I set this thing equal to 0, 0 equals x squared minus y squared. That's x squared equals y squared. So that's x equals plus or minus y, and you get those two lines, y equals x and y equals minus x. And for negative values of z, you're getting these hyperbolas. For positive values of z's, you're getting the hyperbolas on the sides here. Okay. There's essentially three types of things that are really visible. There's saddle points, look kind of like this. The maxes and the mins, the highs and the lows, whatever you want to call them, look either like this or like that. So when I look at Mount Baker, I already pointed out some highs and lows. I could probably pick out some saddle points. Here's a spot where it looks like I got a saddle point in there. Right in here, there looks like a saddle point. Something going on through there. Right, right in here, if that's a little dip right there, there's definitely a saddle point here. Maybe something in here, it's hard to tell. It's a matter of if there's a little bit of a peak right there, then there would be a saddle point right in there. But yeah, I can pick out saddle points, I can pick out high points and low points by looking at those contours. I recognize them. Now there's a couple of different other kinds of things. This is what's called a monkey saddle. There's the z equals y times the quantity 3x squared minus y squared is the classic monkey saddle, which is uphill in 3 directions and downhill in 3 directions. So it is a saddle shape, but it's got, instead of, I think of this one as a saddle for a two-legged rider. But if you have a monkey, you have to have a spot for the 2 legs and the tail to stick out. So the monkey saddle has 3 things, and it's headed downhill towards the blues there, and there, and uphill towards the lighter shades of pale there. One of my favorite surfaces is z equals sine x plus sine y. And here's the contour plot, and here's the graph of some of the surface. It's kind of an egg carton shape. The traces look like sine curves in the x direction and sine curves in the y direction. They're shifted up and down by different amounts, because this stuff is shifting the sines in the y direction, and the y's are shifting the sines in the x direction. So you see these sine curves that go up higher and then down lower, and then up higher and then down lower. Anyway, contour plot looks like this. Notice since I don't have the numbers on it, I can't necessarily tell what level is what, but I know this gets up as high as 2 when the sine is 1 and that sine is 1. So the highest this gets to is 2 and the lowest is negative 2. So down here is the negative 2, up here is the plus 2. In the middle is 0. If you slice this with z equals 0, there are, it's not obvious, but there are lines cutting diagonally through, right through those saddle points. You can see the saddle points here, and I can see them on the grid here. So I've got some high points, I've got some low points, and I've got some saddle points. And that is just one of my favorite functions. Right? One last one, let's just take a look at. 2 things left to do. One is I just wanted to point out the difference between a couple of different surfaces in that these both have circular cross sections here, circular contours, but these are equally spaced. This is a cone. This is z equals the square root of x squared plus y squared, where this is a paraboloid, z equals x squared plus y squared. So this has z increasing quadratically with x and y, and this has z essentially increasing linearly. It's the square root of a square. So it's kind of like linear, and sure enough, the contours are equally spaced as you move out. They're all circular. They're equally spaced. This is a cone. This is a paraboloid. And I can see that it hangs out close to 0 for a while, and then it goes up more steeply on the edges, right? These are closer together contours, and these are further apart contours. So it's fairly flat to start with, and it curls up quicker like a parabola does. On this one, it just goes up at the same rate all the time, and that would be your cone. Right? Last one here, just because it was kind of fun on one of my previous videos where we're just looking at graphs, we came up with this thing of ripples in a pond, but two different ones doing interference pattern. So this is the surface, where this right here is the contour plot. And I can see these long areas of there's a high point right in here, and there's low points down in there. There's a bunch of saddle points along there, some lows and highs, and you can see them, right? You can see these saddle points along this diagonal coming in and down here, right? And you can see high points and you can see low points down in the valley there, right? But looking at the contour plot is a really good way of getting a sense of what a three-dimensional surface looks like by just plotting curves in 2D in the plane. Contour plots. Enjoy.